So this is a worked example of the type that you might potentially see in a final exam. It's a practical example here, and we've been given a setup with an electric fence with a resistor marked B representing the animal. Now you can see at the moment that there's one complete loop and one incomplete loop. So the electricity will flow around the complete loop. When the incomplete loop closes, when the animal touches the fence, then the capacitor will discharge back through the animal. So converting all the electrical energy stored in the capacitor into energy experienced by the animal. So the voltage of the fully charged capacitor, this is relying on you understanding the way capacitors work. So the simple answer is it is the same as the supply voltage. And the reason is that capacitors charge up over time. So when it's first switched on, the charges will accumulate on the plates. Eventually, no more charges can flow. The voltage across the plates is the same as the voltage across the power supply. Therefore, no current flows. Therefore, the two voltages are the same. Of course, you can talk about here, if you want to extend this answer, you could talk about the time constant and how this will take time to happen. You don't know yet what the resistor R is, but you could talk about how you would control the time constant. However, this is a complete answer. This is a perfectly fine, complete answer. So the second part, the animal touches the wire and it experiences a shock. Now, the shock, we're told, has an energy of 10 joules, and we're going to find the capacitance needed to generate this. Now, I don't know on your resource sheet which version of potential energy you're going to be given. The one that I'm most familiar with is that the potential energy in the circuit is equal to a half QVC, where VC is the voltage across the capacitor. And that, as I'm sure you remember from the videos, comes from the Q versus V graph that you can draw. As the voltage increases, so does the charge. And of course, the energy stored in the capacitor is the area under the graph. But, so that wouldn't help us because there's no C in it. But when we know that Q equals C times the voltage across the capacitor, then we suddenly have a relationship where we know all the things. So you'll see I've rewritten that as potential energy as a half CVC squared. You might see this on your resource sheet, in which case this would be a one-step problem, and that's just mathematics. Okay, and we get an answer of 2.2 times 10 to the negative 4 farads. Quite often in your answer booklet, in the answers in the back of your workbook, you see they would have written that as, say, 220 microfarads. That's fine. You can convert or not as you like. Standard form like this is always correct. So now we're looking at number 3, the resistor R. So this is the resistor in the first circuit, prevents the animal receiving too much damage if it stays in contact with the wire instead of jumping back. So electric fences, as I'm sure you know, are designed so that the animal receives a big enough shock that they will leap back from the fence. If they don't leap back from the fence for whatever reason, you don't want them to die from being in contact with the fence. So when the animal is in contact, there is a complete loop, so current can continually flow through that big loop. If R is sufficiently large, the current will be fairly small, hence the animal won't be too hurt. Now, if you have a bit more room on your paper, you could expand that. So if R is sufficiently large, R and B, the animal, are in series with one another, which means that their resistances will add together linearly, and you'll end up with a large R in the circuit. And that large R means small current. Okay, so moving on, number 4, we're told here that, and this one is a little tricky. Like, it took me a few seconds looking at the question. I was like, why are they asking? You know, what are they getting at here? And then the key thing I got at was the 5 joules in a second. So it's giving you a time in which a certain amount of energy has to be discharged for the electric fence to be effective. So how do we know that the animal will be affected? We have to prove that they receive more than 5 joules in a second. So we're assuming that they receive all of the energy and the energy is conserved. Now down here, you'll see I've written 1,000 joules, which should be 1,000 ohms, which I was given in the book. Okay, so that should be 1,000 ohms. Don't make that mistake. So I've written a discharging loop. So the current will flow out of the capacitor and it will run through the animal. And when I work out the time constant of this loop, the time constant of this capacitor while discharging, that will tell me how long it will take for the animal to receive a certain proportion of the charge stored in the capacitor. And what I find is that the time constant is 0.22 seconds, which means, and this is the tricky bit, this is the bit that's not immediately obvious. If you get as far as this, you get as far as finding the time constant, then you're already well on your way to getting and achieved possibly even the merit for this question. This is the important part. 4 time constants pass within the first second. So nearly all of the charge will discharge within the first second. So in the first 0.22 seconds, 67% of the charge will discharge. So by the time you get to 4, nearly all of it is gone. The animal will have received over 5 joules of the 10 joules of energy released. And if you want to, you could work out what percentage those 4 time constants relates to, and you could work out how much of that 10 joules. You don't have to. I mean, you could if you want to. Don't let me stop you. But you don't have to do that. You just have to say enough time has passed that the capacitor will have discharged more than half. So that's an example of the sort of questions that you might see in an exam.